The session that we have now is to focus on the dual core capabilities that we have in the LPC4300 family. And really it's an interesting industry first from an ARM point of view. So the Cortex-M3 has been a very popular replacement, if you will, for the ARM7. The M4 adds some DSP capabilities. The M0 is, I think of it as an M3 Lite. It's a very small 32-bit architecture, small gate count. So what we've done is taken NXP's years of experience with ARM cores and not just created M4, but said, if you want the M4 to do signal processing, why don't you take it the next step and really free it up to do signal processing and have an M0 to do some of the other microcontroller features. And so we put them both in the LPC4300. So I'll spend a few minutes talking about an introduction and explaining what the part is, and then I'll turn it over fairly quickly to Rob to talk more about the technical issues of dual core, how do you communicate between cores, and some of the issues you'd have from a development point of view. Stop me anywhere along the way if there's any questions. Any comments for either of us as we go along? So I'll spend a few minutes introducing the 4300 just to give you an overview of some of the capabilities of the processor. But before I do that, let me mention from an NXP point of view, although we have a history in 8-bit, moving forward we're completely focused on ARM 32-bit architectures. So as we look at it from a Cortex-M3, a Cortex-M4, Cortex-M0, we have a whole host of ARM7 and ARM9 parts as well. So from NXP's microcontroller division point of view, we are completely focused on ARM 32 bits. Particularly in the 8 and 16-bit space, we really see the small M0 as a great replacement. So if you can get 32-bit performance in a small part that's similar in price and better performance than an 8 or 16-bit, why would you need an 8 or 16-bit microcontroller? Now, if you want the lowest possible microcontroller possible, yeah, you're going to still find that in an 8 or 16-bit. But pretty quickly, if you get to the 65-cent level and above, the M0 is really an attractive architecture. So NXP was the first to have this as a general purpose processor. And I spend time on this because it's important when we talk about the dual core later. The difference between an M3 and an M4, anybody, well, just assuming that you're not familiar, the M3 is your standard microcontroller. If you're familiar with ARM7, the M3 takes the ARM7 and adds better power numbers, better performance, better interrupt capability, a whole host of sort of benefits. But it's sort of a next generation ARM7, at least as I think of it. The M4 takes the M3. So you take everything, all the benefits of the M3, and add single cycle multiply accumulate. So it allows you to do cycle multiply accumulate switches for FIRs, FFTs, IIRs, so basically signal processing. Some SIMD capabilities, there's a floating point unit that's added on there. So a lot of benefits if you're doing signal processing. If you're not doing signal processing, as it turns out, there's little to no benefit that the M4 has over the M3. If you're not doing DSP, the M3 will actually do everything you need it to do from a benchmarking point of view. That being said, once we throw the dual core, it sort of changes the equation. NXP's family of Cortex-M processors, we have our 1100 family from the low end and the M0 going to the 1200, which is a newly released family. The 1700 has been very popular, and the M3, the 1300, gives us a bridge to the 1100 and the 1300. There's some pin compatible parts. The 1800 is new. It and the 4300 are also pin compatible. So you can actually design for the 1800 and say, oh, I'd like to add DSP capabilities, and then drop in a pin compatible, upwardly code compatible 4300. So it gives you a lot of flexibility in terms of crossing between family members. All right, so the 4300, we took the M4 core. So anybody can take an M4 core if they have enough money to license it from ARM. We took the M4 core and we added all the peripherals and SRAM and flash, etc., around it that NXP has. So a tremendous history of innovation and IP. But we added some new things. So we think of it as powerful because at 150 megahertz going to higher speeds, it has a lot of capabilities from microcontroller into a DSC space. Is it going to compete with a 400 megahertz DSP if all you want to do is DSP? No, probably not. The strength of it, though, is you get the DSP capabilities and all the microcontroller capabilities in terms of managing USB stacks or Ethernet or all these other peripherals. So the dual core makes it really really interesting because you have a full 32-bit 150 megahertz M4, and we added an M0. Now typically, our M0s run up to 50 megahertz, but because we placed it on the same bus, this actually is a 150 megahertz M0 core. So a lot of performance and capability that you get out of these two cores. Large memories, we actually optimized the memory for some DSP capabilities, so the SRAM is up to 264K of SRAM into multiple blocks. So if you're familiar with DSP, you want to be able to have different blocks you can pull data from. And there's two versions of the part. There's a flashless version that comes out first and a flash version. And for the flash versions, we have up to 1 meg of dual bank flash. And the dual bank flash is a nice feature. If you can assign 1 bank to each core, you can actually have just one continuous block of memory. Or with a dual bank, you can do in-application programming. You can be programming 1 bank while you're executing from the front bank, or vice versa. So some flexibilities there. And we have some advanced peripherals, which I'll talk about. Certainly high-speed USB with an on-chip PHY is nice, Ethernet, LCD controller, etc. We have demos on these in the booth if you want to check out our booth later. So another important focus for NXP, and we have a session in 3:15 today that goes into this in more detail, is what we consider our configurable peripherals. So how do we as NXP differentiate ourselves and make it easier for you, the customer, the developer, to solve whatever engineering problem that you're trying to solve? Well, one thing we thought through is how do you, for example, state configurable timer. How do you design your own state machine or PWMs or timers? It gives you the flexibility to design exactly what you need in your system. The SPI flash interface allows you to memory map a serial interface. Serial GPIO allows you to solve some of the bit banging problems that you might have. And again, consider those as teasers for the afternoon session, but we can talk more details. We actually think of the M0 originally when we place it on there, not necessarily as a dual core part, but as a co-processor to the M4. So we actually originally thought of it as a peripheral. So if you look at the Cortex-M0 as a peripheral and say, well, what can it do for me? I have my M4 here doing all my signal processing. The M0 as a co-processor, as a peripheral, gives me a lot of flexibility. Rob will actually talk from a dual core point of view. There's a lot of ability to make the M4 the master, make the M0 the master, a lot of choices there. So when you partition your code, having the dual core may potentially seem more complicated, but actually it makes it easier, because you can partition your code in the sense that the M0 does all your microcontrollers, your M4 does maybe your data handling or your signal processing code. Pin compatibility with the 1800, I mentioned that earlier. That's certainly a nice feature if you're looking at M3 or M4 capability. Easy is a little bit subjective, but I would say that from our perspective, if you're using a 32-bit processor, if you're familiar with 16-bit DSPs, 32-bit processors are a little more C-friendly. Obviously, the ARM ecosystem is quite extensive, so you have a lot of people who know how to program it. You have people who have a lot of development tools that are out there, et cetera. So we think there's a lot of benefits of the ARM ecosystem, having one tool chain, for example. And of course, we have libraries, free DSP libraries from ARM, and we'll have some from ourselves as well. I talked about this, but just quickly, the M4 core is worth mentioning, and then we'll get into the dual core discussion. Some of the capabilities, this is the ARM slide, if you will, or the ARM block diagram. The dotted lines, if you can see under the memory protection unit, are optional. So everybody who licensed an M4 core can figure out whether to include those or not. To make it easy, we've included everything. So if you want the floating point unit, the memory protection unit, that's all included in the M4. From a family point of view, we have the 4300 family, so we basically grouped it into 4 sections. The dark green is the flashless parts. So if your vanilla parts, if you will, on the bottom are basically all the peripherals except USB, Ethernet, and LCD. If you want one high-speed Ethernet, you go from the 4310 to the 4320 family. You have the high-speed Ethernet, high-speed USB with the on-chip PHY. Going to the 4330, you add Ethernet and the second USB, and going to the 4350, you add the LCD. So pretty straightforward, but gives you some choices, a lot of package choices. Actually, there's not all of them. There's a few more that are coming that aren't listed up there. Any questions so far on the? All right. Just a quick comparison then, if we're looking at the 1800 versus the 4300, what are the differences? We designed these two parts in parallel. We're using as much of the IP as possible to make it as simple as possible for developers to switch between the two. So obviously one difference is the cores. On the top left of either one, not scaled to size, the M4 core is quite a bit bigger than the M3. The M4 with the floating point unit is obviously a difference between the 1800 and the 4300. The dual core, the right-hand side, you see the M0, that obviously is a significant difference. There's a little bit more memory on the dual core, a little more SRAM, which will be beneficial when you have 2 cores. And there's a new peripheral, the serial GPIO, which is only available on the 4300. Other than that, they're more similar than they are different. So if you are developing with one or the other, you can actually make it pretty simple in your system. Pin compatible. If you're writing in C, it's upperly code compatible. There's a few instructions that the M4 has added that are single cycle, but again, pretty easy to switch between the two. So let me stop there. I will stop from the marketing point of view. I'll turn it over to Rob.
Thanks, Gordon. So I'll just introduce myself again. My name is Rob Casaro. I'm the Systems and Architecture Manager at NXP, and what that means is my group's responsible for all the chip architectures that we do, taking some marketing specs that we get from customers and putting that back into our products, also originating our own ideas and putting those into our products. I think we have, within our group, we have over 100 years of experience with microcontrollers, starting with 8051s, now into ARM group. So we have quite a bit of experience with that, with microcontrollers. So anyway, I want to start my talk off with this slide. I think one thing that everybody thinks about with dual core or multi-core products is Intel. And I think that's in most people's minds. If you talk to students, which I do quite a bit of talking to students as well. I gave this talk to the university in Belgrade about a month ago. And when they were talking to them about multi-core, they always think about multi-threading applications, high-end stuff. So what I did was I took and I looked at Intel processors over the years and mapped out the process they're in. And I know a lot of you, don't really care about what process the part's in, but I think if you understand a little bit about silicon processing nodes, you get a little bit of an idea of why we can do things. So I think that's an important thing just to understand from an engineer's perspective of what this means to you as a designer that's using a part in a product. So anyway, as life went on from, let's say, 1988, where I started looking at things, to the year 2001, frequencies went up quite a bit. I remember, oh gosh, that's interesting. It's 1 o'clock. So I remember back in the day when we had single core processors running at 200 megahertz was a big deal. And then as we moved on, frequencies went way up. And then like 2006, you got to over a gigahertz processors. And then things stopped, right? CMOS can only go so fast, right? You can't make it go any faster because just it's the way CMOS works. Now, I'm not saying that's going to continue on like that, but for now, it looks like we're stuck at about 3 gigahertz or so. So what did they do? They went and they said, let's put more cores into the processor. So we'll get more work done for the same task by spreading that workload over multiple cores, right? So you can see more and more cores coming into processors. It creates a software problem, right? Because now you have to say, how can I do multi-threading? And that problem's getting solved in certain ways. I think Windows 7 now has support for more multi-core applications. Linux had it for a while. But again, this is a more high-end problem. And that's not what we're trying to solve. What I wanted to show you here is that as we go down these process nodes, it allows you to put more stuff in there. And I think that's something where as a system architect, whatever, we're finding that as we go down these process nodes, we have to think of more creative ways to use the silicon. We do not want to waste silicon, right? It's such an important resource. I think that's all driving cost. It's all about die area, right? So as you go down these process nodes, you have more silicon area, and we have to figure out what to do with it, and we have to make it useful for our customers. Oh, where's my other slide? Oh, that one. So symmetric processing. Let's go back to that one. That's a big problem. There's caches involved, and you have maybe level 1, level 2 caches, definitely level 1 caches, and you have to worry about cache coherency, requires an OS support. And there's this Amdahl's law, right, where you don't get 1 over n speed up, right? It's always said that as you increase the number of cores, I can just divide the number of, the speed by number of cores, and that's what speed I should expect, but that doesn't happen, right? Because you can't multi-thread certain things, right? They have to happen in one processor, so you don't get that kind of speed up. And there's a problem with communications as the number of cores increase, how do you communicate simultaneously for all cores? It doesn't work very well. So anyway, we're not talking about that in our case. So when I talk about process nodes, as far as NXP is concerned, I put this graph down because I thought it was kind of interesting, and it kind of gives you an idea of gate density versus process node. So when I started working at NXP, we were in a 0.35 process node, and before that we were in 1 micron. And this is the feature size. This is the size of the channel of the transistor. And as we drop down in this feature size, we can put more and more stuff in there. So at 0.35, the densities were somewhere around 10 to 20 kgates per square millimeter. And about 2003 or so, we went to a 0.18 node, and that's about 50, 60,000 kgates per square millimeter. And now we're in a 90 nanometer node in this 4300 process. And that is about 250 kgates per square millimeter. So you can see it's almost, from the very beginnings when I started, more than 10 times increase in gate densities. Now, when we make our parts, there's this thing called, it's a term that I never understood until I started working in this field. It's pad-limited designs, right? So you want to make something that's kind of on the pad-limited, core-limited kind of regime. What that means is I have the most amount of pads around the die, and that kind of tells you how big the die is going to be, and how much stuff can I put in that area, right? So you try to make it so it's really kind of pad limited, and that's what we always try to do. So in 90 nanometer, it's really easy to make a pad limited design, and there's like all this area, and what are we going to do with that? So then we started thinking early on is let's do this idea of asymmetric processing, and I think that could be a really interesting idea for this 90 nanometer node. So it's not really intended to do distributed tasks. I mean, you could do that in an application kind of sort of way, but if you want to do processing, we're not going to support multi-threading necessarily. You could do that on your own. And I don't know what's going to happen in the future, right? There could be some ideas that we come up with that would allow this to happen. But in this case, this asymmetric core idea, and like Gordon talked about, and I'll talk more about it later in the presentation, it's really about dividing up the application amongst the two different cores. It's not really multi-threading necessarily. So we have separate program resources for each core, and there is no really specialized OS required, and I'll talk more about that as we go on. And also simple hardware for processing communication, trying to make it easy. And I think that's something that, to think about this asymmetric idea, this has been around for a long time. I read a paper from, I can't remember, Amdahl or something like that, talking about in the 70s, talking about asymmetric processing. And we're just taking it and integrating that into one monolithic silicon that's available to the general market. NXP has been doing this for quite a long time in our car radio division, where they have processors devoted solely for software-defined radio, and then they have other processors devoted to other things. So if you look at in the history of NXP, in other areas, we have, I think one processor I saw from NXP had like 10 cores in it. But you can't get that as a general market part. It's not possible. Because it takes too much support, right? You just can't go and buy it. If you're let's say GM or whoever making car radios, yeah, you can get it, but not as a general market part. So our intention is to have this available to the general market. And stop me at any time if you have any questions. You don't understand what I'm saying. I had a comment once. I used too many acronyms maybe sometimes, and I expect you guys to understand. If you don't, let me know. Okay, so I'll talk more about, Gordon touched upon this a little bit, but I'll add a little more depth to it. We started doing stuff with ARM 7 in 2003, and we had a product called LPC4106. And then life went on, and everybody's got to make more money somehow, and things got to get better. So ARM decided that they're going to change their instruction set from ARM thumb kind of idea to a thumb 2 instruction set. So you didn't have to worry about the switching between thumb and ARM. And that led to the Cortex-M3. And then, that was about, 2005 or so, I guess, when M3 first came out. We started adopting that in 2007, 2008. We weren't really happy with the M3 necessarily because it was such a big such a big core, really, for like trying to do 8 and 16-bit replacement ideas. We had the LPC2103 that was based on ARM7, and we were always pushing ARM for a smaller core. They came out with the M1, which is kind of interesting, but it really wasn't suited necessarily for standard cell place and route. It was more suited for FPGA. So we worked with them in 2008, end of 2008, 2009 on definition for the M0. And my group was involved with that. Now we have a nice, small, tiny core. It's based on the thumb instruction. It's still like thumb 2 compliant, right? Because if you look at this little green box in the corner down here, that's the M0, M1 instruction set. And you think about thumb instruction, that means 16-bit instructions. But there still is 32-bit instructions. The most important one is the BL instruction, the branch with link. But basically M0 is a thumb machine, right? And there's only like 40-some instructions. Then as you move up into the M3, there's more. And then as Gordon said, the M4 adds all these DSP instructions. So now we have this great family of processors that are consistent. They're just, maybe one's a little bit more powerful than the other one. So the M0 is a really perfect core for this kind of dual core application space idea, right? So that's why we picked the M0 to apply that to our M4 product, because it really makes sense as far as instruction set, simplicity of use, and all that kind of stuff for our asymmetric core. So I just want to point out the flexibility of having this continuous family of products, right, from M0 to M3 as far as M4 as far as cores are concerned. In addition, the fact that instruction sets are consistent, code is consistent. So when we did the 4300, and I don't have a slide on this, and it's going to come out as we get it more to the market, we have ROM code in our parts. And the ROMs are fairly large in the 90 nanometer process. We have plenty of opportunity to add code that's useful to the user. So what we did was we compiled everything to thumb, the M0 instruction set, so it can be used by either core, which is kind of cool, right? So I said, well, let's say we have a USB driver or USB stack in ROM. So either the M0 could use it or the M4 could use it. You're not really stuck with just having the M4 using it. So I think that's kind of a byproduct of the fact that we have this continuum of cores available. It's really a key point to think about. Then you'll say, well, what's the advantage and disadvantage of just going to thumb only or thumb 2 instructions? Well, you lose a little bit on performance, but sometimes really who cares on some of these application space ideas? It still runs just fine. But that's just ROM code. You're always free to add whatever code you want to in Flash. Okay, so from the viewpoint of the asymmetric implementation, we have the M4 and the M0, and they have a link between them, so they can communicate to each other to say, look, something's happening here or something's happening there, and they have their own program memory spaces. So it's not like we're trying to thread things, right? It's really, you have to really think about this idea as 2 independent cores on a monolithic piece of silicon. And if you think of it that way, it kind of opens up all kinds of different application space ideas that you might have. When we first came up with this idea, this was not driven by customer input at all. It was something that we thought up as a group. We've been kind of pushing this. Like I said, we have a lot of silicon stuff, a silicon area. What are we going to put in there? So we started talking to key customers about the idea, and they thought, wow, this is really cool. Look what we can do with this now. And you're going to see, there's going to be a lot of people, coming out with dual cores, I'm sure, as life goes on, but in the general market space. But I think the idea of making it simple at first was what we thought would be most valuable in this area. And think of it as really 2 separate application processors that can communicate with each other in an easy way or simple way. Okay, so as far as simple, so we have this word goes out all over the time, this IPC. You hear IPC, IPC. Interprocessor communication, what does that mean? And you can have hardware support for it, where you have this cache coherency idea, with big cores sharing a cache or trying to operate out of a dual cache. And it gets complicated, and you need hardware support for that. But for our IPC, what we've done is we've taken the cores and we've hooked them up with interrupt lines. M0, M4 have an output port called transmit event. It's called TEXV. And there's an instruction, send event instruction, that creates a pulse on this port. So there's a separate instruction that you can issue to a core to send a pulse out that goes into the NVIC of the other processor to give you an interrupt. And that's really the interlink between the two cores. It just interrupts. That's what it really is. Now the IPC part of it is really done in software, and we kind of leave that up to the user to come up with his own IPC if he wants to, he or she wants to. We will provide what we think is a simple IPC, and it's going to be in ROM, and you can use our IPC if you want. If you don't want to, you can use your own. And we're going to extend that into an operating system where you'll have two operating systems running, and one can be running its own application, and the other one can be running its other application, but they can communicate to each other with services. So that's what we're working on now, and you'll see that coming out as we get more production silicon. We have stuff running in our lab. We're trying to productize the software. So the idea is that you have an SRAM, and this is just general purpose SRAM within the part, and you divide it up into a command buffer and a message buffer. And who is the master? That's up to the user. You decide who do you want to be the master. Like, let's say you want the M0 to be responsible as the communication processor and then offload all the calculation tasks to the M4. That's possible. Or if you want to have the M0 be the peripheral controller of doing something interesting that way, you can have it as a slave. So it really depends on your application. And I think that's something that Gordon touched on. Is we're not trying to dictate how your application should work, right? It's really up to you because you know better on your application than we do. And that kind of goes back to the idea of soft or flexible peripherals. We give you a lot of options, and you can decide how you want it to work in your application. I know this creates some kinds of complexities because, what do I do? And we're trying to solve that problem with giving you a simple IPC, lots of examples of how to use it, and I'll go through those as the talk continues. So in IPC, what's important? Well, synchronization, right? When I talk to you, you can't talk to me at the same time or we get confused. So we live in a physical world, and even silicon has the same problem as humans do, right? So we always have to honor these communication channels, and they have to be synchronized and they have to be coherent. So like I said, IPC is done in software with read and write pointers, and the intention is to have a buffer that you specify and a size. It's up to you how big you want it to be, and you tell it where the start and end addresses are, and then a pointer into that memory space for messaging, sending it back and forth. And the hardware connection really is just the idea of interrupt sources from a separate instruction, right? It's not like you have to give it an interrupt where you have some latency there. You have to stack stuff. You say you give it an instruction. You say send event, and it'll go ahead and interrupt the other processor, and then you go and query any messages that come back from the other processor. So that's really how we intend to do this simple IPC. We're going to learn a lot as we go on with this, and I know already there are some questions, comments, concerns about how we've done the implementation, and I can give you some things that we're thinking about based on feedback that has come from the field. One has been the idea of memory partitioning. I don't have any slides on this, but I'll talk to it. And what I mean by that, or memory protection, I should say partitioning. I talk about partitioning, I mean protection. So if I have the M0 doing something and I have the M3 doing something, how can I prevent one overriding its own memory space? Well, we kind of leave that up to you guys to solve in your software. That's something that it's not hard to solve, but in hardware. But we're going to leave that up to you in the initial parts. But the M4 has a memory protection unit, so you can region its memory and protect its memory. But the M3 can go in and trounce on it if it wants to. Or the M0 can go in and trounce on it, I'm sorry. There are some thinking in the future that will have M0 protection too, so we're working on some hardware mechanisms to prevent that, and that'll be on future parts. But again, we're learning as we go on with this. We have we think it's a great solution we have right now, and I know there's going to be things that we're going to improve upon as we move forward. The other thing is kind of watchdog timers, if one process gets stuck, you want the other one to continue running. We didn't think that was such an important area of concern that if one application fails, really it's the whole processor, the whole chip that needs to be reset. So you really have one watchdog timer. That could change in the future. So there are some, there are a lot of things when you start talking about asymmetrical dual core ideas within a single piece of silicon that you can just go crazy on the protection or the IPC and all that kind of stuff. But we wanted to keep it relatively simple at first. Right? And I think that's a good strategy to start with. Okay, so let's look at the chip. So when we draw as a architect group, when we look at the part, the matrix, the bus infrastructure is such an important part of performance that we kind of have a special way that we draw it, and a lot of people are adopting this method. I've seen this show up in our competitor slides, which is kind of interesting. But we always put the masters on the vertical lines, and the slaves go on the horizontal lines. And whenever you see a dot on this fabric, that means that master has access to that slave resource. So as an example, so you can see this 72 kbytes of SRAM is available to both the DMA controller, the Cortex-M0, and the M4. So both processors have access to that memory. The dot indicates also that there's arbitration there. So if the M4 and the M0 try to access this 72 kbytes of SRAM, there's no contention, there's no confusion, it's just some delay, right, as the arbitration happens. And that's kind of transparent to the user. But if you look at it, look at this drawing, the M0, where's my cursor? The M0 here and the M4, they have separate slave resources, right, as far as memory is concerned. Let's look at the memory right now. Actually, I think I have another slide on that. Yeah, let me move ahead. So let me talk about the memory model. But each processor has the ability to address a memory independent from the other one. And I think that is a key point in the architecture for this multi-core operation, because you don't have contention. Each one has its own path to a memory resource, and it can execute from that memory resource. It doesn't have contention, but it's up to you to allocate those resources correctly, right? So if you want the M0 to execute out of this SRAM, the 128 kbytes of SRAM, you can put your code there and say execute from here, and give the other SRAM, the 72 kbytes, to the M4, right? So they're independent, there's no contention, they both have their own memory resources. If you wanted to give more to the M4, you can. You can do vice versa, whatever. So I think that's another key part of this architecture, is that there really are a lot of resources available to either core, and it's up to you in your application how you want to divide those. And that's, again, more flexibility in the application space. I talked about, let's see, the ROM. We talked about the thumb issue, the M4 and the MPU. So you can protect the M4 code, the M4 from trouncing on M0, but not vice versa yet. Just move back here. So we talked about the memory, but what about the other stuff, right? Like the peripherals. How do you allocate the peripherals to the M0 or the M4? Again, it's the same kind of idea. Is where we have a pretty, we call it a pretty luxurious matrix in this part, where the M0 or the M4 has access to peripheral layers as well. So we've divided our slaves into, and when I mean slaves as far as peripherals are concerned, we always put those on an APB interface, and you can ask me, why do you do that? Why don't they sit on AHB? Well, the answer is, we want to have them operate at different frequencies, for one, and typically slaves don't need to have this AHB kind of access where we can go as 8 or 16-bit or 32-bit words. Slaves are always accessed in these parts as a 32-bit peripheral. It just makes the interface much easier to deal with. So if you look at how the slaves are architected, there are 5 different regions. And let's look at adapter. We call it an adapter. This is a bridge between AHB and APB. It's something that you don't have to worry about so much as a user, but as an architect, we think about it in these ways, that there's different, we try to put resources, spread them across these different APB bridges in order to avoid contention as far as performance is concerned. So taking an example, adapter 3 and 4, we've divided the UARTs across those two different buses. You know, we could have said, oh, screw it, we'll just put all the UARTs on one side, you know, all the SPIs, just as, you know, randomly throw things in there. We don't do that. We do a lot of thinking about how we should partition the slave resources, right? So we'll have SSP0 and SSP1 on different adapters, and the reason why we do that is M0 could be talking to SSP0, M4 could be talking to SSP1 with no contention. You know, they're directly associated with those processors. And I think that's the thing you have to get, you know, when you start looking at your application, you can define the resources to the particular processor for that particular application, right, with no contention. So, you know, I wouldn't, as an example, oh, I'm going to say M0 has UART2 and M4 has UART3. That wouldn't really make too much sense, maybe, as far as contention is concerned. You can do it. There's no, and I always say contention is a bad thing. It's just a performance thing. You can still do that, no problem. But, you know, if they're both trying to access the peripheral at the same time, one's going to be delayed versus the other one. So anyway, so we always try to balance the peripherals across these different adapters. Okay, so apart with Flash, how can we use Flash in this dual core mode? So a flashless part, we'll talk about how the boot goes with a flashless part, but, you know, you'll allocate a certain portion to the M4 and a certain portion to the M0. With a part with Flash, what we've done is, as Gordon said, we have two banks, and they both have their own flash controllers. They both have a instruction and data bus. So what that means is M0 can operate out of one flash, M4 can operate out of the other flash with no contention. So that's one way to do it, right? You can also, if you wanted to, operate in a contiguous mode and have M4 operate and M0 and M4 operate out of the same flash. There's going to be some contention, but maybe you don't care. You know, it's just a performance hit, right? Maybe you don't care at all. So it really just depends on how you want that to work. Now this is not part of this talk, but I'll touch upon it. This part will operate in excess of 150 megahertz, and how do we do that with Flash? Flash inherently is relatively slow, and the reason why Flash is slow, it's a high voltage device, and the capacitances are large. If you look at merchant Flash these days, you know, the guys that you can just go buy Flash from whoever, access time is somewhere between 50 and 60 nanoseconds. They're getting a little bit faster as life goes on, but, you know, they're always going to be slower than SRAM. There are ways to improve performance, but the power consumption goes way up. What we do is we have very wide flashes, and in this case, they're 256 bits wide, and so we can get to these really high frequencies with minimal latency. We have a special interface that does some buffering that gets you within 5% performance of SRAM. So there is some performance penalties by having these wide flashes, because if there's a miss, because it's really not a cache, if there's a miss, you'll have to do another fetch, but we do some prediction and things like that prevents that from happening. So anyway, that exists for both the M0 and the M4. The M0 can operate at the same frequency as the M4, so it's 150 megahertz M0 operation, 150 megahertz M4 operation on this part. We talked about that one. So this slide illustrates what I was talking about earlier, that there's these separate paths for in the matrix for operating each core from the memories. So that's, I think, again, just to reiterate, this is a really important concept to get across to people, that, you know, we have these flexible interfaces. So this is how we intend the part to boot. There's ROM code that does that starts things up. So the M4 starts up first, and we have on the flashless parts a bunch of different ways to boot, a bunch of different boot options. You can boot from all the different interfaces. You can even boot from USB if you wanted to, right? So we allow you to do a bunch of ideas of booting within ROM, and you select that. There's different ways to select that. One is via pins on startup. When you do a reset, the boot code looks at pins and how the pins are configured. That'll determine the boot source. Some people don't like that so much, so there's a way to override the pin and say hard code the boot option. right? They don't want to use the pins because maybe they're GPIO pins or something like that, and you want to use them for your application, and it's difficult to use them that way. So we allow you to override that with an option, even in the flash list part. And how we do that is we have some non-volatile memory in the flash list part. It's write once, so once you do it, you're kind of stuck. So you better get it right at first. So you can't change it. On the flash-based parts, you can change it. So the M4 starts up first, then you can then move code into the M0 domain, how you ever want, whatever code that you want the M0 to run, and then start it up, right? So really the M4 on boot is going to be the controller, the master controller. I guess we could have chose the M0. I think M4 made most sense to us because at the time when we thought about this, the M4 was supposed to be the master processor, and the M0, as Gordon said, was like a peripheral controller. That's our initial concept, right, that we had, that it was going to be a peripheral controller. But as life went on, we said, oh, no, let's make it really just general purpose. That makes more sense, right? So we kind of changed our minds a little bit early on in architecture, and we said, well, just keep M4 as the master on boot. So it makes sense to us, I guess. So anyway, so M4 will load M0 IPC, encode, start up, things start executing independently and running independently after that with IPC communication. So that's the intention. So let's look at like application space ideas. How can this be used in an application? And I know you guys will probably think about a lot of different ones, but these are some of the ones that have come up in our endeavors. And one is for audio processing. Like the M4 is really good at doing filtering and stuff like that. And it takes a lot of work to get your filters correct, right? All your algorithms. Then all of a sudden somebody says they want to do some kind of communication protocol, whatever. And well, do I have enough processing power with the M4 to take care of all this other stuff that needs to be added? Well, you don't have to worry about that with this dual core approach, right? You can keep your algorithms for your audio processing, whatever process you have, in the M4 domain, and then have the M0 worry about the other additional add-on stuff. In this case, we're talking about I2S communication, taking the audio data from the M4 and then putting it into the I2S channel to play or record music and things like that. And also, you can do USB communication. Oh, look at that. 130. So you can take the USB peripherals and have the M0 worry about USB communication using the stacks in ROM as well, right? So we have right now in the ROM there's DFU code, there's HID, mass storage, and there is going to be some host stuff in there too. So we're trying to put as much as possible into the ROM code to make it more useful for you guys without having to go, where am I going to get the USB code as an example? So anyway, this is one case, and this shows the partitioning in the hardware, how that would work. So there is, again, separate resource directly to SRAM where it's doing its audio processing, and the M4 has separate resources into the USB block, and also to the APB peripherals where the I2S block lives. So there really is no contention there, and the dual lines into this SRAM indicates this is where the sharing is going on. Another example, which I think is an interesting one, is motor control. Again, you're spending a lot of time worrying about your algorithms and your closed-loop control for motors, and you're not worrying about how am I going to communicate with the application. That's a whole other layer that you'd have to add on, and you're always worried about, resource as far as performance is concerned. I'm always worried about, do I have enough time to complete my motor control task before I have to execute maybe some kind of communication task, right? So then this partitions, this gets rid of that problem where the M0 then can take care of the communication task, and then when the M4 is ready to accept the data from the channel, it can go ahead and grab it and then change the motor speed or whatever, or dynamics, whatever you want to do in this application. So here's another case where partitioning it makes a lot of sense, where I'm concentrating the M4 on the DSP motor control application, and M0 is worrying about communication. In this case, we're showing CAN as the communication control. And again, it shows kind of the idea that there are separate resources M0, M4 has in the system, your overall system. You know, you can do this with separate pieces of silicon. You know, that's been around for a long time. You know, I can take, you know, a part with CAN and I squared S or SPI, and I can use SPI as the communication channel. That's fine, but you don't get the immediacy. You know, you don't get that really tightly coupled, low latency performance as you do with a single piece of silicon. Okay, last thing I want to talk about is debug. And you say, oh, this is always something that you need to have, or else how am I going to make my part work? Like, debug is really important. So what we've done in this system is we have the M4 and the M0 on the same JTAG chain. So when you start the part up in your debugger view, you'll see two cores. You'll see the M0 and the M4 will show up. But they're treated as separate cores. For now, we don't allow lockstep debug, you know, single-step debugging where they're both lockstep. They're really independent cores. Now, I think this is adequate for what we're trying to do in this case, because we want to treat them as separate applications, not, you know, multi-threaded applications. So you'll have two views within your IDE. Within one single view, you'll have the M0 and the M4. And when you want to debug the M4, you'll have the M4 change focus, and it'll be the active debug window. And if you change focus to the M0 will be the active debug window. Now, for cross communication problems, you set up your own breakpoints. You break one, and the other one will break two. So you'll have this idea of breaking completely on a breakpoint within the M4 or within the M0. So that's really useful, right? But as far as single-step debugging, that's not implemented within this architecture. That's something we were looking at in the future. We'll have to see as people start using it more, and some of the maybe improvements we could make in the future. The M4 has full trace. So you do have full trace on the M4. It's not shown in this diagram, but there's a full trace port. And there are a lot of low-cost trace tools out there these days. And I encourage you, if you can afford trace, buy a trace unit, because it really makes life much easier. I have a guy that works in my group that came from Know-How, and he designed the ARM trace pods back then, and he's really good at using trace. I give him a problem, he solves it within an hour. I give it to some other guys that use start-stop, you know, breakpoint debugging. It takes them 3 days. You know, so it's really powerful using trace. And I know it's something that always was a cost-prohibitive thing, but you know, now from various tool vendors, IR, Kyle, and all, you can get the pods for like $1,000, I think, or less these days, and it allows you to do full trace. And all of our M4s that we have in the field, or will have in the field, will have trace capability, and we really pride ourselves on, you know, putting the most trace features in our parts. The M0 never came with trace. That was never the intention. When we specified M0, it was supposed to be a low-cost core, no trace, not even serial wire debug trace. I know that could change in the future, but for now it doesn't have it. I don't know if it's that important, but definitely for the M4, for doing stack development and things like that, and algorithm development, having trace is a really nice feature to have. So that's why really M4 is a key part of trace. Also, the M4 has, in our parts, we allowed to have 16K allocated in one memory bank for trace data. So if you don't have a pod, you can put trace data into the memory. Now, it's always hard to get trace working at full speeds, right? But having a trace buffer in the part that can operate at full speeds allows you to do a pretty decent job of tracing for 16K of code space. And we're going to make that available on our LPC Expresso platform. So trace is coming in, you know, this trace through just a JTAG port is coming to LPC Expresso. So I think that's something that'll allow people to use it effectively for very low cost. Okay, so there was a demo, I guess, at one time. It's
in the show floor.
Yeah, so you can see what we tried to do on this demo to show the independence of the M4 and M0. The M0 is controlling one motor, and the M4 is controlling another one, and they can sync up based on when you point the laser through a hole. It gets the information about where the plates are, and it'll just start rotating coherently. So it kind of shows you there's kind of independent control of the different motors. So anyway. So any questions?
2 more slides.
Oh, 2 more slides we have? Okay.
Yeah, I'll trade.
Okay, oh yeah, so Gordon is,
Just a couple more marketing slides for you, but more of kind of the getting started for you. And just a comment on the demo. So that dual motor control demo is on the show floor at the NXP booth. Take a look at that. We mentioned audio as being in a market segment, if you will. This is interesting. There's a very interesting audio demo you can go look at. One of our partners, DSP Concepts, has done a graphical tool for audio. So you put the graphical tool, you draw all the blocks, you press the button, and it actually programs the board and runs. So there's an audio demo that shows 98% utilization of the M4 core, which is great, except now what if I want to add a USB stack? Well, that's where the M0 comes in. The M0 in that demo is not being used, but it shows you the capabilities from audio point of view. There's also a demo showing the floating point unit capabilities. We haven't really talked about that, but there's the floating point unit, floating point capabilities. And we talked about dual core debugging. Code Red, another one of our partners, is there showing you dual core debugging. So those are all there for taking a look for you. If you haven't already, our website hopefully has some useful links for you in terms of online training. We have this LPC zone, so videos, etc. This video, in fact, will be posted at that site probably within a week or so. So there's more videos that we've done from other sessions that might be worth checking out for you. And then if you're interested, you can follow us on Twitter. We have a YouTube with some small videos there as well. And we have a support group on Yahoo Groups. It's actually maintained by, it's external to NXP, but it's focused on NXP microcontrollers if you're interested. Okay? Thank you everyone for coming. We'll be available for questions. And there's another session on peripherals at 3:15 if you're interested. Thank you.